Today we're going to talk about a couple very different topics from chapter 21 and 22. I'm going to start off with the photoelectric effect, which, if you did your vocabulary the other day, you should know at least a little bit about. Photoelectric effect. This has to do with kinetic energy and frequency. And I'll just give you the formula to start off. The kinetic energy maximum that a photoelectron can have is equal to Planck's constant, h, which we'll talk about in a second, times the frequency, minus Planck's constant times the threshold frequency for a particular piece of metal. Now, Planck's constant, like it sounds, is simply a constant. And this constant is equal to 6.63 times 10 to the negative 34th. And this is measured in joules seconds. So 6.63 times 10 to the negative 34th is Planck's constant, so it's going to go both of these places. Now, you can pretty easily mechanically just plug in here. If you have kinetic energy, these h's are both constants. The only thing you may get confused about are F and Ft, frequency versus threshold frequency. So let's talk a little bit about that, and kind of try to give you a little bit more of a conceptual understanding here. F is the frequency of light. Ft is the frequency of metal. And so what's happening here is we've got some piece of metal, and light is shining onto it. It's being hit by light. The photoelectric effect says that tiny particles of light can then be ejected from the metal. So particles of, not exactly light, particles of, they're photoelectrons is what they are. So they get ejected from the metal. Now this equation talks about how much energy these particles have for a certain frequency of light and a certain threshold frequency of metal. So given a particular metal, for which this will be just constant, we'll know what the threshold frequency is, and given a certain frequency of light, we can find the energy with which these particles are expelled from the metal. And it's a weird kind of otherworldly woo sort of thing, but this is a real physical phenomenon that happens. If metal gets hit by light at a certain frequency, photoelectrons jump off it. And it's absolutely a strange thing. So just bear in mind that F is the frequency of the light, Ft is the frequency of the metal, and of course kinetic energy is the amount of kinetic energy that's happening here. So it's a fairly simple equation. You guys have gotten pretty good at the basic algebra here, but I wanted to talk at least a little bit about what was happening here in case you didn't read the textbook passage there very carefully. Alright, so that's that. Let's move on. Next, let's talk a bit about quantum physics. Now, we've talked a little bit about it before. It was on the Elegant Universe. Those of you who actually watched that, you had to do a few definitions on it earlier. But the basic idea of quantum physics is that sometimes light acts like it's a wave, and sometimes it acts like it's a particle traveling through space. Sometimes it acts like it's a wave of energy, sometimes it acts like it's made of matter. That's really the fundamental idea behind quantum physics, because you can't, it's the conflict between which is it acting like right now. There was a scientist named Louis de Broglie, and I'm not sure that I'm saying that correctly, who said, well, if light sometimes acts like a wave and sometimes acts like a particle, maybe matter also sometimes acts like a wave and sometimes acts like a particle. And so he called these matter waves, this idea. And we have a couple of equations that we can do that relate to this. And this is pretty high level stuff, and I'm not too concerned with the really subtle fundamental understanding of the concept here. So I want you to be able to do the calculation. I want you to have seen it before. So a couple of things. First, de Broglie said that the wavelength of a matter wave, lambda, equals Planck's constant, which we talked about earlier, divided by momentum, which we could further write as Planck's constant divided by mass times velocity. So this was the first thing that de Broglie suggested. And that's pretty easy to do. If you have one of these, you can have two of these, you can solve for the other. Not so bad. The second thing that he said, if we talk about wavelength, we can also talk about frequency. He said that the frequency of a matter wave was equal to energy over Planck's constant. So we see Planck's constant here again. So these were really simple. And the questions aren't real hard either. It'll be really obvious what's going on. So if we're talking about the wavelength or frequency of matter waves, here are the formulas for that. Wavelength and frequency. And last today, I want to talk about one of the most famous equations in physics that you don't always even get to talk about. E equals mc squared. Yeah, this is, you think about the theory of relativity, you think about Einstein when you see this. And this is used for several things. As it's written right here, it's called the formula for rest energy of a mass. But we're going to talk about the binding energy in a nucleus. So a different form of this would be E sub bind would equal delta M times c squared. And this is the binding energy is equal to delta M is called the mass defect, not the mass effect, the mass defect. And c is of course just the speed of light. Now, what do I mean by binding energy? This is actually the energy that holds the nucleus of an atom together. And the mass defect is a lot more complicated. This delta M is kind of deceptive because it's not just MF minus MI. There's a fairly complicated process you have to go through to find this, which we won't do. I'll just give you the mass defect. So this will be a pretty easy equation for you to use, and I just wanted to talk about it very briefly here so that you would know one of the things that it's used for. You could sound really smart one day. If someone's like E equals mc squared, you said, oh yeah, you can use that to find out the energy that holds the nucleus of an atom together. And people will think you're really smart even if you're not. And that's an important skill to have, sounding smart. So that's all we have for today. I'll have a few of each of these types of question. And that's it.